So now coming to problem number 7. So here in the reaction, they are telling you to find the x. This is x, and you have to find it. So here I have you have been remembered that I have told you about the ozonolysis reaction, right? So when a alkyne or alkene is actually treated with this ozone, what happens? Ozonolysis takes place, and the second they have added dimethyl sulfide, so it will basically cleave the ozonide that is formed in the reaction. So what is the mechanism? I'm again recalling the mechanism here so that you will get what I'm talking about. So here, when O3 addition takes place to alkene, what happens? Molozonide first forms. So this molozonide being very unstable, so it will get cleaved to give you these fragments. Again, these fragments will recombine to give you the ozonide, which is stable. And in the second step, they have added the dimethyl sulfide, which is used to cleave this particular ozonide to give you the reduction products. Right? I hope you remember all the things because I've talked about the ozonolysis reaction and mechanism previously. I'm not going into it. So here, one by one, we will go to each alkene. This is one, this is two, and this is three. So let's say if I'm talking about alkene number one, what happens? If you cleave this alkene bond, then you will have this carbonyl here, again this carbonyl here. And if you see it very closely, this is the ketone. So this is acetone. So this is what which is matching here. So you will have this moiety from this cis substrate. So now if we are figuring it out what it is, then you will be thinking that here there is a proton present, right? So it is not a ketone, it is a aldehyde, and this aldehyde is attached with this link chain. So now it will not give you a separate fragment from the chain, but this ketone is the separate fragment from the chain. So here this ketone is coming from the alkene number 1, and you will left with this CHO molecule here. Now coming to alkene number 2. Now if you cleave this, again you have two hydrogens here. Again you have two hydrogens, right? So you will be having a carbonyl here and a carbonyl here. Right? So there will be two carbonyls. So if you see, this is what formaldehyde looks like. So here also you have given the byproduct as formaldehyde. But here this is the ketone because both the side it is connected to carbons. That is why you will end up having one side ketone and another side formaldehyde. So this formaldehyde is the fragment which is detached from the ring. So here you will get it as a byproduct. But this ketone is present in the ring only. So that is why it is not getting detached. Now coming to this. Yeah, coming to this 3. Now if it is getting cleaved, again you have two hydrogens over there. So now you will again find a formaldehyde moiety here, and this is also a ketone. Fine. So now here also one H is present. That is why you will have a CHO and again a formaldehyde moiety from this side. That is why you are getting two molecules of formaldehyde. So one formaldehyde is coming from this alkene number 2 and another formaldehyde is coming from alkene number 3. This acetone is coming from alkene number 1. So now just erase all the things to get a better vision. Here what you will end up with is this. So here you will have a CHO coming from alkene number 1. Here you will have a ketone that is coming from alkene number 2, and again here you will have a CHO coming from alkene number 3. Right, this part is attached to this particular chain, but these fragments is getting detached from this chain. That is why you are getting it as a byproduct. So here one by one we have discussed how this alkene is going to react with ozone, and you will get a product that is this. So now tell me which will be the correct option here. The correct option will be option number what? Option number 2. So this will be the correct option, right? Fine. This will be the correct option. Right. So coming to problem number 8 now. This problem number 8 we have discussed in the case of alkenes, the hydroboration reaction. So they are talking about the major product form in the following reaction sequence is. So you have to find out the major product that is going to be formed in the following reaction sequence. So when you have treated this alkene with BH3 and THF, what is BH3? Borane. So one thing you have to remember is borane in the borane, this boron is electron deficient and these hydrogens are electron rich. So now this alkene will attack to boron and this H minus leaves out. So now this hydrogen is not going to be knocked out as H plus but as H hydride ion, H negative. So here this alkene will take up this boron, and I have told you it can be done by two ways. If this carbon number 1 take ups or carbon number 2 take up. So if carbon number 1 take up the BH2, then the carbocation is getting formed at the second position. So second position carbocation is a tertiary carbocation. Whether if the second position carbon will take up the boron, then the positive charge that is getting created at the carbon number 1 will be the what? Secondary carbocation. So that would be the secondary carbocation. So here a secondary carbocation is getting generated. That is why the alkene carbon number 1 will be taking up this boron and this hydride that is H minus. Here you will have H minus in the system. This H minus will then attack onto this carbon number 2. So this is how it works. This is the particular mechanism how it is going to be done. So first of all, this carbon number 2 will take up by the boron, take the boron, and then the hydride will attack the second carbon. But there is a catch. Here, the addition of BH2 and the hydride will be from the same side, because the BH3 is a planar molecule and alkene is facing to BH3 from a significant face. So if it is attacking to boron from one side, then also hydride again will be attacking on the alkene from the same side as well. So the addition is syn addition. So the addition of BH2 and H from to the alkene is what? The syn addition. So that is why you are getting here the syn product, not the anti. So this is very important to consider that the addition is same side attack is going to take place. Okay, now this is sorted from the first molecule. What first condition? What you will get is you will get a BH2 here, just writing the alkene part. You will get a hydrogen here, and this Me was already there, right? This is Me. This Me was already there. So here you will get a BH2 at this position. Here you will get a hydride, that is hydrogen at this position with the saturation now, because here alkene is converted into alkane. So this kind of moiety you will get. like this. Now they have added in the second part, they have added hydrogen peroxide in the presence of NaOH. So this, what this hydrogen peroxide do? This hydrogen peroxide in the presence of NaOH, this OH minus will take up the proton from hydrogen peroxide, giving this system, giving this particular species in the system. So now this species will then attack towards this BH2, this boron, this O minus attack to the boron, giving you this particular species. So the migration of CB bond to oxygen takes place. So this CB bond will migrate to this oxygen. So protonation then takes place. So first of all, then what happened? The attack of NaOH on OBH2. So migration is happening from this CB to CO. So CB bond is getting cleaved and CO bond is getting formed. Again, the NaOH which is present in the system because the system is basic. So here this OH minus will then attack on the boron and then it will form the oxygen. This oxygen will again get protonated by the water and you will get this particular alcohol. At the place of BH2, now BH2 is getting replaced by OH. So this is very simple. Only in the second step, what is the oxidation? The BH2 is converting into OH. But the stereochemistry is not going to change. Stereochemistry is fixed in the first step and it will be going forward in that condition only. So here, what you have, first step hydroboration, and second step is oxidation. So it is known as the hydroboration oxidation reaction. So here, what we have gone through is this particular moiety. You have understood how this HBH2 addition takes place in the same fashion, then the deprotonation. So here we will got this. Now after oxidation, this BH2 will be this BH2 will be gone. And what will happen? This OH comes here instead of BH2. But the stereochemistry is fixed. So now you have to look at in the option, you have to look at those options where the stereochemistry of hydrogen and the OH is same, because only those examples or those products give you the particular right product. So if you see here, this is hydrogen that is above the plane. So here also the stereochemistry is same, so it could be our product. But now coming to second, there is above the plane H, but OH is below the plane, which is not possible because the attack is syn, and in the oxidation step there is no stereochemistry change. So that is why it could not be our product. So it is getting eliminated now. So here coming to option number 3, here the stereochemistry of hydrogen and the OH, it is syn. So it could be our possible product. Now coming to option number 4, again here it is below the plane. The hydrogen is below the plane but OH is above the plane. So the configuration, the stereochemistry is anti, so it could not be our product because the addition is syn. So here amongst 1 and 3, our product can be 1 or 3. Okay. So now here there is a stereochemistry difference. So here what happens, this ring, the stereochemistry of this ring plays an important role. So here as you can see, the ring stereochemistry is above the plane. So above the plane ring is there. So there is a steric hindrance if the addition of H and BH2 will take place from above the plane. So it will feel a steric hindrance. So to avoid that steric hindrance, hydrogen and OH will find it comfortable to come from the below side. Understanding? See, what I'm saying is, first and second, third, both can be the answers, right? Both the stereochemistry is same, location of OH and H is right. But what you need to know, the secondary thing is that amongst these two, only one can be the answer, right? So if you have to judge from 1 and 3, so you have to see the stereochemistry of the ring as well. So if the stereochemistry of the ring is above the plane, then the hydrogen and BH2 will find it more easy to attack on that alkene to add to the alkene from the below the phase because of the steric hindrance. So that is why the option number 3 will be the correct one. So option number 3 will be the right answer, not the option number 1. So I hope it is clear. Just take 2 minutes to understand what I am saying. See, I'm summarizing the things up. First step will give you the hydroboration. Hydroboration will lead you generation of the BH2 at this position and hydrogen at this position. So after having this intermediate and the oxidation will then give you the BH2 replaced by OH. So now if BH2 is getting replaced by OH, that the stereochemistry is not going to change. So the attack is same, stereochemistry of H and BH2 is same, and the OH which is getting replaced by BH2 is also sent to the hydrogen. It is clear, right? So here, if these both are sin, then what happens? First and third could be the possible answers. But here we are seeing that we are seeing that here the steric hindrance also plays an important role. It is above the plane. That is why the H and BH2 will prefer to to add to the alkene from the below side. So that is why option number 3 will be the correct one. This will be the answer. Right. I hope it is clear now. I'm moving forward to problem number 9. So here in the problem number 9, they are asking addition of BH3 to a carbon-carbon double bond is anti-Markovnikov sin addition, anti-Markovnikov anti-addition, Markovnikov sin addition, and Markovnikov anti-addition. So addition of BH3 to a carbon-carbon double bond, that is the hydroboration reaction which we have talked basically here. So is it the anti-Markovnikov sin addition, anti-sin, or anti? So I have told you it is a sin addition. So wherever you are finding the anti word, just eliminate that particular thing because it is not an anti addition, it is a sin addition. So among these two, you have to figure it out. Is it anti-Markovnikov or Markovnikov? So here Markovnikov rule I have previously discussed. It suggests that the negative part of the addendum should be add to that carbon of the alkene which is bearing lesser hydrogens. So if you have to add HBr onto this particular propine, not propine, let's say this propane. Let's say this is propane, right? So now if you have to add this particular HBr onto this, then what happens? Here the carbocation will be generated here and Br will be attacking onto this, right? So Br will be adding to that part of the alkene, that carbon of the alkene which is bearing lesser number of hydrogens. That is what Markovnikov rule is suggesting. So here, if we see in the case of BH3, the negative part is adding to that carbon only, which is having the lesser number of hydrogen. That means it is adding to that carbon which is more substituted, right? Which is more substituted. So here it is following the Markovnikov sin addition, not the anti-Markovnikov, because anti-Markovnikov suggests that the negative part will add to the lesser substituted carbon. That is the terminal. If Markovnikov addition is to be taken place, the product for this reaction would be the 2-propane, 2-bromopropane. But if the anti-Markovnikov rule has to be exist in the presence of peroxide, then the product for this reaction will be 1-bromopropane. Okay, that is why it is suggesting this is what the Markovnikov anti-Markovnikov rule suggests. So now here you have to figure it out, the addition of BH3 to carbon carbon. So here the negative part is this hydrogen. It is adding to which carbon? Which is less, bearing less number of hydrogen, that is more substituted. So that means here also the negative part is going to add on the carbon which is more substituted, having the lesser number of hydrogen. So it is following the Markovnikov sin addition, not the anti-Markovnikov sin addition. Fine with everyone. Any queries, any doubts? Why it is anti-Markovnikov? Why it is not Markovnikov's in addition? See, anti-Markovnikov suggests that the one bromopropane is going to be formed, but Markovnikov suggests that the negative part will go to that carbon which is having a lesser number of hydrogen or this is more substituted. So here also, if we are going to figure it out about the hydroboration to the carbon-carbon double bond, it is also one kind of Markovnikov because the hydride, that is H minus, is adding to the lesser substituted carbon here. Okay, so that is why the correct option will be the Markovnikov synadation. So is it clear to all of you? Any doubts? Okay, then I'm going to problem number 10. So problem number 10. Here, the hydroboration of 1-methylcyclohexene using D2D6-THF deuterated diborane followed by the treatment with alkaline hydrogen peroxide gives what? This is the step 1. This is the step 2. This is the hydroboration oxidation reaction only of 1-methylcyclohexene, that is this compound. I have told you instead of this diborane, they have taken the deuterated borane. Okay, so instead of hydrogen, it will be having deuterium at the place of hydrogen. Sorry. So at the place of hydrogen, you will having a deuterium. Similar mechanism is there, similar everything. Just hydrogen is replacing deuterium, right? Sorry, deuterium is replacing hydrogen. So now what happens if you have this boron with this D? This D is also what? Negative. That is the partial negative charge and it has a partial positive which is electron deficient. So now again similarly this alkene has to add to boron. So now it will be adding by two phase either carbon number 1 either carbon number 2, and by the time you all have know that it will be adding from carbon number 1 because the positive charge then which is creating at the carbon number 2 is much more stabilized than carbon number 1. So due to the stability of carbocation, we are saying that carbon number 1 is attacking towards the boron. So, so boron is getting attached over here. We did 2, BD5, anything. Right, so here what boron is getting attached. Now another positive charge is captured by deuterium. So what you will have now in the product, sorry for the poor drawing, I couldn't help it. So here you will have that BD2 and here you will have instead of the hydrogen you will have a deuterium. So this is what you will get as a product. But now in the options, as you can see, you have to mention stereochemistry as well. So the mechanism I'm again explaining. First of all, boron, boron hydride is sorry, hydrogens are electron rich, boron is electron deficient, alkene will attack to boron, in turn hydride will attack on the same phase, so the syn addition takes place to give you this molecule. Again hydrogen peroxide and attack onto this particular boron to give you this migration product. Again the migration, after migration the NaOH will attack on the boron to give you this oxygen ion which taken the proton from the oxygen. So here how this is how you will get a alcohol in the place of BH2, OH is getting placed. So this is how the mechanism works. So after having this product in hand, now you have to mention the stereochemistry. Now what will be the stereochemistry? That is the major question here. So here I have told you that deuterium and this BH2 BD2 will be syn to each other. This addition is syn. So you have to figure it out that particular substrate which is having a syn addition. So all the things are having the syn addition actually. So one by one we will go through it. So here hydrogen is there. So where is hydrogen is coming from? So there is no hydrogen in the system. That is why we can say that it is not going to be attached here. This the position should be deuterium. That is why it is getting neglected. It couldn't be the answer, right? So now coming to option number two, the place of deuterium is now wrong, because if you generate a carbocation at this position, then it would be a less stable carbocation, that is the secondary, and here the tertiary carbocation generates. That is why this is also not possible. This is not the answer. Both the deuterium are going to be added. No, it's not the particular hydroboration mechanism. Now coming to this part, this is what the possible this is what the possible product. Why? Because here deuterium and OH positions are right. The syn addition is reflected, so that is why the correct option will be option number 4. So option number 4 will be the correct answer. So is it clear to all of you? Okay, if it is clear, then I'm going to problem number 11. So guys, this will be the last problem for today's lecture. So I hope all of you have understood what I have what I have taught till now. So if you have any problem, please comment and tell me. Okay, so the problem is dash is produced when one equivalent of HBr is added to one hexane. So I have drawn this hexane structure, and now you need to know that only one equivalent of HBr is added, not excess. It is only one equivalent that is added. So now this is the hexane, and this is the main mechanism which I have showed you earlier. But there in the first problem, the HCl was in excess. So I have told you that the excess and one equivalent, it actually makes a huge difference, because the product which you are getting for both is different, right? So here one equivalent is present. That means only one mole of HBr is there. So if one equivalent is there, that only one addition will take place. Neither that second addition will not take place, because for the second addition HBr is not there. So now what happens? Again the similar procedure. Instead of Cl, you have a Br here, right? Again the alkene take up the proton from the carbon which on which the carbocation is stabilized. So here the secondary carbocation is more stabilized than the primary one. That is why the internal one is getting generated. After that, this Br minus will attach to this carbocation, and to give you this alkenyl chloride or alkenyl. Now in the case of this, it will be alkenyl bromide. It will be alkenyl bromide. Right. Now the addition of second equivalent. Will it be possible? No. Because when you are talking about the excess substrate, then you can say yes, the addition of second equivalent is possible. Fair enough. But when you are talking about the one equivalent of HBr, then the addition of the second equivalent couldn't be possible, because there is no HBr that is available in the system. So here, if you are adding HBr, taking in the mind a similar mechanism, now this hydrogen will be taken up by this terminal carbon. Positive charge get created at this position. Br will then attack on this positive charge. What you will get is, what you will get will be this hydrogen. This will be Br, right? So now just name the compound for me. What will be the compound? It is one. Sorry, it is 1, 2, 3, 4, 5, and 6. Then it would be 2 bromo hex ene. So it will be 2 bromo hex 1 ene. So after reacting one equivalent of HBr to hexane, what you will get is 2 bromo 1 hexane. That means the second option is the correct one. But if you have the excess of HBr, then again another set of Br will get attached here, and you will get, instead of alkene you will have a alkene. So in this case you will get a 2,2 dibromo 1 2,2 dibromohexane, right? Simply. But because the one equivalent of HBr is present here, that is why you have the limited addition, that is one addition. So you are getting this 2 bromo 1 hexene instead of the 2,2 dibromohexane. Fine. So this is it for today. I'm closing the session because I hope this is clear to all of you. This much is clear to all of you. So thank you so much, guys, for listening. And I'm just closing the session. We will be meeting on next Saturday, this coming Saturday, 6 to 8. That is the time which we take up the sessions. So here I will be uploading this particular video on my YouTube channel. So you can go through this video once again. If you haven't understood anything, any step, anything is not clear, you can go through it and can ask me in the next session or in the comment box, wherever you find comfortable. So thank you so much. I'm closing the session now. Thank you so much for attending the lecture. Thank you so much. Okay, bye.